Good evening, everyone. Welcome, welcome, welcome to 60 Minutes in Space. My name is Jessa Phillips. I'm the coordinator of adult programs here at the museum. And I am so thrilled to be back in person for this monthly event. Yes, applause. It's so great to see everyone and see this space community again. So we're so excited to have you back. And we also have a virtual audience joining us tonight. So hello to everyone watching virtually. We're excited to have you too. I am so excited to introduce our speaker tonight. I think many of you DMNS regulars know her, Naomi Pequette, an adjunct professor of astronomy now at DU, and owner and chief scientist for Peak Nova Solutions. Naomi worked with us for many years and is one of the most engaging and awesome space scientists and science communicators that I've had the pleasure of seeing. So thank you all for coming, and please welcome Naomi Pequette.
Well, thank you, Jessa, for that all too kind introduction. And thank you everyone for being here. I'm also excited to do in-person events because my virtual events happen with my basement and my green screen studio. So it's nice to get out and actually see faces as well as squares on the screen. So as Jessa said, my name is Naomi. I'm an astronomer and I'm a science communicator. So it's my job not only to help move science forward, but make it fun and exciting for all of you and make it accessible to the public. So I'm doing that through my own business called Peak Nova Solutions, as well as being an adjunct professor of astronomy over at the University of Denver. So if any of my students are watching, hello, welcome back. So the goal of tonight, obviously, is to catch you up on the most recent space science news from this month. And we can't not talk about the James Webb Space Telescope, JWST. So just a quick refresher, JWST is NASA's new flagship space-based observatory. It was advertised as the successor to Hubble because it can see deeper and further into the universe. It is an infrared telescope, which we'll talk about what that means in a second. And one important thing, because of this wavelength, we've got some new requirements. We've got a beautiful sunshade, and we are not orbiting Earth. We are out at a Lagrange point, which is a stable gravitational point between the Earth, Sun, and Moon system. So not really serviceable. So can we just say hooray for the engineers that made this crazy contraption possible? It is amazing. So the scientific objectives obviously peer deep, far into the universe. That's the one everyone knows about. But we also want to study the atmospheres of extrasolar planets, study our own solar system here as well, and study formation of stars and planets as a whole. And so I'm going to try and pick an image that hits each of those scientific objectives. We're not going to get through all of them tonight. Otherwise, you would be here for a couple of hours and I would be geeking out with you. But I want to cover a lot of other stories as well. So what is infrared? So how many of you are familiar with the electromagnetic spectrum? Okay, a lot of you, awesome. So kind of a quick overview. The universe puts out a ton of electromagnetic radiation, and generally we're going to call this all light. A very, very small piece of this in the middle is visible light. That's what our eyes see. So when we're looking at this graph from the left, we start with very, very short wavelengths of light, really high energy, and move to longer and longer wavelengths and lower energy. So infrared is just past the red part of our visible spectrum. And by looking in different parts of the spectrum, we can get different pieces of information. So we'll start with an Earth-based example here. Everyone looks at their hand, right? If you look at your hand here, we're using visible light, we're using our eyes. We can see surface detail, right? We can see that I'm wearing some cool nail polish, my skin, my finger length, wearing some jewelry, things like that. Now, how many of you have had an X-ray before or know of an X-ray yet? Okay. Right? Are you seeing the same information? No, right? We're seeing then through that surface. So we're looking at a higher energy, shorter wavelength of light to do that. And for anyone who's ever been in Space Odyssey or stood in front of a thermal camera, you've seen yourself in infrared. So this person here is very much like me. We've color coded it. Blue means cold, so they've got really cold fingers like I typically do. A nice warm palm there. So we see more information, and together scientists can piece these together to get more information about a whole system. And we can do that with things like the Crab Nebula. This is a supernova remnant. None of these are JWST images, but we've got a beautiful Hubble image of the visible light. X-ray lets us see that energetic pulsar at the middle, and then we can peer through some of the dust in infrared. So infrared for us is really important to be able to peer through dust. We have a lot of dust and gas hanging out in our cosmos, and that can get in the way of us seeing, in particular, star-forming regions. So that's really one of the reasons we want to look in these particular wavelengths. But infrared will also allow us to do something pretty darn cool. It allows us to see further back to the beginning of the universe, towards the beginning of the universe. So I'm going to make a statement, and I'm not going to really go too in depth about it, but as objects move away from us in the cosmos, it appears that all galaxies are moving away from us as our universe expands. They get redder. So there we say their light is redshifted. So those wavelengths get longer. We see this visibly. We see it in their spectrum. So by looking past those visible wavelengths into infrared, we can see further back in time, further away from us in terms of those first galaxies, and peer back. Because astronomy is cool. We're time travelers, which I think is pretty awesome, right? The further away we look, the further back in time. But James Webb's also assisted by the fact that it's huge. It's made of 18 segmented mirrors, 6.2 meters across, compared to Hubble's just over 2 meters. And so that gives it 6 times the light gathering capability of Hubble. So think of telescopes as big light buckets, right? The bigger your bucket, the more photons you're going to gather of light. So really an impressive look into the universe. Now, one other thing I want to point out, we just said this is infrared light. So this is light beyond what our eyes can see. And so to be able to portray this information to you, we've had to do something called false color these images. Hubble did this as well. And I want to show you with an example of Saturn how this is done. So here's a true color image of Saturn from Hubble. And what they do is they take images through different filters. These are called broadband filters because they cover a good chunk of light, but it doesn't matter. And they measure the brightness. And then we assign a color to each of those filters, combine them, and we get a colorized image. So we might be doing this with James Webb with the near and the far mid-infrared. For example, it might be specific wavelengths of light that tell us about emissions of certain gases. And there is a logic. We're not just randomly assigning colors, right? We try and highlight things that make sense to us. And so why do we even do this? Well, first of all, it's way more fun to look at a color image, right? It's more intuitive to understand. It's visually dynamic. And just by looking at color values, we can get science out of that sometimes. It's also, frankly, a good thing for public buy-in. If we released a bunch of black and white images, it wouldn't be nearly as cool as those great, sexy Hubble Space Telescope images, right, with the full color. So it is also important to colorize for that reason as well. So you've heard a lot, or at least I have in the media made of, these are false color images. It's okay, we're not trying to lie to you. We're not trying to do like pull the wool over your eyes in any sort of way. But this is what we're doing. So we're taking measurements through different filters and colorizing them. Okay, time to get on to the fun stuff. Should we look at an image? All right. So this was the very first image released in that press conference with President Biden and Vice President Harris of a new ultra deep field, if you will. So what we're looking at here is a cluster of galaxies. This one here is the center of our cluster called S Max. We'll have to look at the number 0723. Real exciting name, I know. So the light from this cluster left 4.6 billion years ago. So you can kind of think of a galaxy cluster in terms of our cosmic address. If our galaxy is our house, right, we then have a local group of galaxies. In the case of the Milky Way, it's literally called the local group. Again, exciting. And these are gravitationally bound. So that's like your neighborhood, right? Your subdivision, if you will. And a galaxy cluster is like your metro area. These are large collections of galaxies that are gravitationally bound to one another through all of the stars and gas, but also dark matter and other cool stuff. And so we can see a ton of things in this tiny section of sky. So these are huge, huge structures, but on our sky, it takes up the space of a grain of sand held at arm's length. And we can literally see thousands of galaxies here. So I want to look at just a few of these galaxies because I got to download the full resolution image. I spent a lot of time just zooming around. And there's a lot that can be learned just from digging into this. So on the right, I pulled out a handful of my favorite spiral galaxies. So spiral galaxies are like our own Milky Way. They have nice spiral arms. They're kind of intermediate in terms of mass. And so we have a huge variety. Up here in that upper right, we have a barred spiral galaxy. So that center is not just a sphere, it's a nice bar with two distinct spiral arms coming off of it, not unlike our own Milky Way. We can see a spiral galaxy edge on here. If you think of the Sombrero Galaxy, a really famous Hubble image, is a great example of an edge-on spiral. This one is just got some beautiful, beautiful spiral arms. I also love that this is closer, it's dominated by blue light. And this tells us a lot about the stars there. Spiral galaxies have a lot of stars forming in them, and they're dominated by hot, young blue stars. And so they tend to appear more blue in color if they're not redshifted. So we got a great one there. Someone told me its name is Miranda. So don't know if that's true, can't verify that, but it's what I've been calling her. And then down here, this is one that really reminded me of the Triangulum Galaxy M33, just some really nice, tons and tons of spiral arms there. So we've got some great spirals. We also have some big elliptical galaxies. Elliptical galaxies tend to be more massive, older star populations, not a lot of star formation. So of course, we've got the big honker at the center of this cluster, but there's some others. So these are kind of spheroidal, elliptical, kind of cigar-shaped, not exciting particularly, but interesting scientifically. And then even maybe some interacting galaxies. So galaxies do very slowly gravitationally interact. It's not quite like a collision here on Earth, right? They'll slowly pass through one another. And let me say, I have a lot more sympathy for my students. I made them do an assignment like this for a lab in class where they had to go through and identify galaxies, really zooming in. I'm sorry, that was fun and rough all at the same time. But of course, we also have these weird looking arcs that are coming through there. To understand that, we need to understand a concept that we call gravitational lensing. So nothing but the finest clip art graphics created for you all here. So a galaxy is pretty democratic. It gives off light in all directions. And if nothing is in between us, the observer, whether it's a cute little telescope here on Earth or James Webb Space Telescope, whatever it might be, it would look like it would just pass through. Light wants to travel in the shortest way possible, and that's a straight line. But one of the consequences of general relativity is that huge amounts of gravity curve space and time, and that can bend light. Call it lensing light. And so this galaxy's light, as it hits this big gravitational mass of a globular cluster, or excuse me, a galaxy cluster there, would be bent around it, probably also magnified and distorted along the way. And if we looked back, it would look like the galaxy isn't here, but it's maybe over there, and maybe over here, and maybe down over here and over there, right? So an experiment you can do at home is actually take a wine glass, a stemmed wine glass, put it over some graph paper, and you'll see how those lines warp. Or just be very, very careful if you do this at home with a laser pointer. Don't shine anything into anyone's eyes, right? If you line it up well, you can get a laser pointer down the stem of a wine glass and you can actually see those arcs of gravitational lensing, similar type phenomena there. So very similar to what we're seeing here. Gravitational lensing is hugely important to us because we can learn so much more about more distant galaxies. So here's an example of a gravitationally lensed galaxy. So to orient you, there's that big central galaxy there. And one thing I forgot to point out, these big blue spiky things, these are stars in our own galaxy. Because they are pinpoints, light is not diffuse spread out, it ends up spiking because of all those hexagons that are on James Webb's mirror. And they're working actually to be able to limit some of that diffraction spiking in future processing. So stay tuned. So that's not a galaxy there. But okay, so we're looking at some of these wispy objects. Here's some gravitational lenses. And Dr. Karen Sharon, who is a professor of astrophysics at the University of Michigan, actually went through this image. She has been doing computational modeling on this particular galaxy cluster for a lot of years. And so she's intimately familiar with it. And so what scientists can do, and what she's done for us here with her nice colored arrows, is go through and find distinct features and match them up. So these two images are of the same galaxy. But these that were back kind of over here, that look very similar, actually have some distinct features, and they aren't the same galaxy. So painstaking, but you can definitely do this and identify these individual galaxies. And there's even more of these. So this is a result from her computational model. This is a Hubble Space Telescope image of the same cluster with the results of her computation on top of it. So what she's done here is label several features. Pink and blue circles are where their same galaxy is imaged or lensed multiple times. Green is where they would be located if that gravitational lensing hadn't occurred. Cyan are galaxies that are in the cluster. This is what's doing the lensing. These are galaxies that are only 4.6 billion light years away from us. And then the red is marking where that gravity is coming from to do that lensing. So it's not only luminous matter, it's not just these galaxies, but it's also a lot of dark matter in there. So this gravitational lensing is really cool because now we can learn about the mass of this cluster. But we can also take images like we saw here and de-lens them. And because now they've been magnified, have been made larger by this gravitational lensing, we can see further back in time and further away in space than we could without this phenomena. So really crucial in multiple ways. So to give you an idea of a difference here, this is the James Webb image, the Hubble image of the same area. So just look at that much more detail that we can see how many more galaxies are visible, the coloration because of that detail we can get. But James Webb didn't just image these galaxies. They also took spectra of 48 of these galaxies. So spectra are like fingerprints. They can tell us what an object is made out of, what elements or molecules are there. And from that, they could see how far those spectra have been redshifted, so shifted over to those longer wavelengths. And that can tell us about when that light was emitted. And one spectra showed that the light was emitted 13.1 billion years ago. That is just a few 100 million years after the Big Bang, the origin of our universe. It's not the furthest back we've seen, but it's still pretty impressive. And I'm not the only one sitting there zooming into this data, staring at it, going, whoa. There's a team from the Harvard Smithsonian Center for Astrophysics who spent 2 weeks straight pretty much doing this. And in one tiny little section, I, for the love of goodness, could not tell you where in this image the larger context this is. This was the biggest context I could provide you. But they found this little red fuzzball of a galaxy candidate that they named Glass Z13. If you're familiar with astronomy, instantly you'll go Z13. That's telling me something about the distance. That's a redshift number. And so what they did was they looked at the color of this. They took very much more detailed measurements than we are, saying, wow, that's really red, right? They can qualitatively measure color. And based on that color alone, they say this galaxy candidate's light was emitted 13.5 billion years ago, just 300 million years after the Big Bang. This might be the most distant galaxy we have ever observed in humanity's life history. Now, they're careful to call this a galaxy candidate. There have been 3 papers released in the last week on a website called Archive that kind of pre-publishes astronomy papers, analyzing the light from this galaxy candidate. But ultimately, we need to do more observations to confirm this result. We need to take a spectra of it. We need to measure that redshift really precisely. And they're already applying for more James Webb Space Telescope time to be able to observe this. But already, check. Observe the most distant regions of outer space. First image, James Webb knocked it out of the park, right? JWST was amazing. Okay, so the next one I want to look at is not a cool image, but really important scientifically. So JWST also released some observations of an extrasolar planet, a planet orbiting another star called Wasp 96. This particular exoplanet was discovered in 2014 by the transit method, which we'll talk about in a second. It's about 1,500 light years away from Earth. And it represents a type of planet we don't have in our own solar system. It's something we call a hot Jupiter. So this is about 1/9 of the distance between Mercury and the sun. So it's orbiting very, very close. It orbits around in every 3.4 days. But it is about 1,000 degrees Fahrenheit from that. And it's 1.2 times larger than Jupiter with half the mass. So big, puffy, hot, weird planet. And this is what we got from it. Doesn't look exciting at first, but as a scientist, I promise you, I'll explain to you why this is really exciting. So what this is a spectra. So that is our wavelength here, brightness here, that tells us what the atmosphere of that exoplanet is made out of. And we've detected water vapor. So really exciting. So how do we do this? Well, this planet's orbited in a really specific way that means it passes in front of its parent star once every 3.4 days, 3.34 days. So that transit that we saw, right, we can see that it dips that starlight in brightness. So this is brightness here, time. So there's the light of the star, it's doing its thing. The planet passes in front of it, dims it down, and it brightens back up as it passes across. And so JWST monitored the star for 6.5 hours, took 280 brightness measurements. We have about 2.5 hours before the transit, and an hour and a half afterwards. So just this is cool. This tells us that we were right on the size and the orbital properties of this planet as it is. But the fact that this star's brightness dips, it's only like 1.5%, but it dips, means that we can also look at the light that is coming from that star, its spectra, during or before and during that transit. We can compare what light we see coming through it. And so this was done with the near infrared imager and the slitless spectrograph, and it looked at a huge, huge span of wavelengths of light into the red, into that near infrared. And starlight filtered through that planet's atmosphere, and some of it got absorbed. And it's different molecules that will do that absorption, and what wavelengths of light that happens at tells us what molecules or elements are there. And so we found water vapor because of these huge amounts of wavelengths that we were able to look at. And so if we were to apply this to an Earth-like planet, this would be massive, right? So this is really a technological demonstration. So what we found is that there is water vapor, but it's less than we thought there would be. So that means there must be some sort of level of clouds hanging out in the atmosphere of this exoplanet that's blocking that water vapor. We also find that there's this kind of weird gradual downward slope off to the left. And that indicates this is a really hazy atmosphere. We have some sort of haze hanging out in the upper atmosphere. And this particular planet was keen for this kind of observation because it was so puffy of an atmosphere. It was extended out. It's fairly large, short orbital period. But ultimately, we want to do this with extrasolar planets. And the fact that we are now able to, for the very first time, observe light, this kind of 1 micron on, and get detailed spectra out of it means we can look for water vapor, we can look for oxygen, and we can look for other key indicators of habitability and possibly even life. So now that we know it's possible, they're going to start turning towards more and more difficult targets. And we should be able to see even more details coming soon. And so there were several more images released. And after that initial rush, there's a really quiet release that happened. And they released through the Space Telescope Science Institute a lot of images and spectra of objects in our own solar system. So it's pretty easy to look at one point in space far away and hold that position steady for a while. But when you have objects closer to you, like objects in our own solar system, they whiz by pretty quickly. So you need to have really accurate tracking and be able to move that telescope pretty nimbly. And so the team started doing observations of Jupiter, several small asteroids, and they found we can do it. And we can do it with high resolution. So they released this image of Jupiter. So on it, you can see these iconic bands and stripes that are on Jupiter. We see in visible light. That famous great red spot, that big storm, that's hurricane-like storm. And then we also have its moon Europa and the shadow of Europa hanging out on it. But that's not what's exciting. What's really exciting about it is the faint details that we could see. So when we kind of blow out the surface of Jupiter, you can see Jupiter's ring, which was discovered by Voyager by looking back towards our sun. This is a really faint infrared object. We also see a couple other faint moons. So now we know that we can track this telescope quickly and still get really high resolution data, because now this telescope can turn its eyes to the icy far outer regions of our solar system that don't typically emit a lot of light, and use that infrared light to give us even more information on comets, Kuiper belt objects, asteroids, and even more objects. So an exciting thing that we have the flexibility to observe the furthest reaches of our universe and our own home solar system. And then I wanted to throw this one in. This just came out a couple days ago because I thought it was darn cool looking. So this is being called the Phantom Galaxy. This is M74, Messier 74, or New General Catalog 628. Real exciting names. I can see why they're starting to call it the Phantom Galaxy there. So this is what we call a grand design or perfect spiral galaxy, and we're looking at the center of it. So here is the core of this galaxy, which probably houses an intermediate black hole, size black hole, and then these really beautiful, perfect spiral arms coming off of it. And so this is about 32 million light years away. It's located in the constellation Pisces. It's something you can see with a pretty big amateur telescope, although not quite like this, unfortunately. And for comparison, here's what it looks like in the visible light. This was with a ground-based telescope from the European Southern Observatory. So there's that core of our galaxy, and there are these spiral arms. You can see it's really dominated by that blue light. Those are hot, young blue stars, recently, cosmically speaking, still millions of years old, stars that are hanging out there. But you can also see there's a lot of dust. So these dark areas that you're looking at aren't where there's nothing, but where there's so much that light can't get through it, at least visible light that we can see with our own eyes. And so with the James Webb Space Telescope, what we can do is peer through that dust, especially when we're looking and combining that near and mid infrared, which is what this image does, and look into those regions where stars are forming, and those clusters of where stars are forming. So this is part of what's called the FANGS survey, or the Physics at High Angular Resolution in Nearby Galaxies. So what they're doing is they're building this huge data set to be able to study how do stars form, both in contemporary galaxies and galaxies further out. So they've used Hubble, they've used the ALMA radio observatories down in Chile. And with James Webb, with JWST, what they're doing is they're actually trying to survey 19 nearby galaxies and look specifically at star clusters and these star forming regions to tell us more about how stars form in our contemporary universe. And they released several other images as well, so I encourage you to take a look at them. They also processed this image a little differently, highlighted a specific wavelength of light that showed some molecular emission that was cool and very purple. So more of this is going to come out. This is going to be opening a floodgate of data that we're going to start seeing. So stay tuned, because I think we're just going to have new scientific discoveries announced pretty rapidly with each new image that comes out. Okay, it kills me. I want to talk about all the images here. But there is more to space than JWST, I think. And so I want to turn a little closer to home and look at some of our own solar system events. So Curiosity turns 10, yay. That's my bad Photoshop there for you. So August 5th, Curiosity will have spent 10 Earth years on Mars. That's over 3,500 sols or Martian days, so about 5 Martian years, exploring Gale Crater, which was this ancient lake bed. And it's incredible that it's still going. It's limping a little. It's got some metal wheels that are really torn up, and now they're imaging every 4 hours. So not so great there, but still functioning, still rolling. And on June 7th, it actually went into safe mode for a little bit. A spacecraft will go into safe mode basically to say, something's wrong, I don't know what it is, but I don't want anything else to happen. And so what they saw was that they thought there was an instrument control box that was much, much warmer than they expected it to be. 2 days later, they found we could turn it back on. It's probably a false reading. We still don't know. But a decade out in the harsh area of space is not too bad. And it's still providing good science. So it's hanging out, taking some samples in this lovely area here, which is called Yellowknife Bay. And the release from this month is that we measured the total amount of organic carbon in these rocks. We did chemistry, yay. Okay, why is that exciting? So organic carbon is carbon bound with hydrogen, right? And it's the basis for all organic molecules. And it's created and used by all known forms of life. So remember, the whole idea with Mars is follow the water, find that we can prove that there was once a good environment for life to have possibly existed there. Perseverance is taking us further. But this discovery of organic carbon is really exciting because they found it was 200 to 273 parts per million, which is comparable to low life areas here on Earth. So something like the Atacama Desert in South America. There's still life there. Maybe not my top choice to invest in real estate unless you are building an observatory, then it's great. But this is way more than we've ever detected in Martian meteorites, which are the samples we've been able to study here on Earth. So really possibly exciting, but it's not proving the existence of life because it could come from volcanoes, it could come from several other non-organic sources, and maybe even be formed by surface reactions. But we didn't even have a baseline to know if there was enough of it in the rocks to indicate that it was at about the same level we see here in really harsh environments on Earth. And it is. So one more data point that we keep adding to this, saying Mars was a different place. There could have been life. There could have been life. No smoking gun yet. No Marvin the Martian lighting a birthday candle for curiosity, but there we have it. And we should get even more data coming back soon. So just today, NASA released new information about the Mars Sample Return Mission. So if you remember, Perseverance actually had kind of 3 missions associated with it. We have the Perseverance rover itself, which is lessons learned from Curiosity and built upon it. We have the Ingenuity helicopter, which is just breaking all expectations of what we thought it could do. It was supposed to be an engineering test. Maybe it would fly a handful of times. And it actually delayed the start of Perseverance's mission because we're like, oh, let's keep playing with the helicopter. It's doing good stuff. Right? And then we have this Mars sample return. So the idea is that NASA and the European Space Agency are going to collaborate to bring the first samples back from Mars. And we've done this with comets. We've done it with asteroids. In fact, the sample from Bennu and the OSIRIS-REx mission should be back next year, which is pretty darn awesome. But now from another planet, we can have samples that our more complete laboratories here on Earth could really analyze. And so they actually have just finished, NASA has just finished looking at all the system requirements of what it would take to bring a sample back from Mars. And they added in new information about the success of Ingenuity and better understanding of what that lifespan of Perseverance is likely to be. And so they just finished what they call the conceptual design phase, where they really go through all of those system requirements with a fine-tooth comb and make sure it is what they want it to be. And they announced some really significant changes to the plan. So for up until last week, NASA was saying they're a little nervous. They don't want to send just one lander. Got to send two. One is going to have a fetch rover on it. So a little rover that's designed to go grab the samples that Perseverance is collecting and dropping off all along Jezero crater, bring them back to the Mars Ascent Vehicle and this robotic arm that the European Space Agency is going to build. And that is what will get launched up into space. But because Perseverance is doing so well, and Ingenuity is doing even better, they've ditched this fetch rover from the plan entirely. And so what they're going to do is use Perseverance as that primary means of going and collecting those samples that it's been dropping around, bringing them back to that Mars Ascent Vehicle and their sample retrieval lander. And they're also going to send two helicopters up that are based on Ingenuity's design that can act as backup sample retrieval. Now, one of the things I didn't get an answer for, I was like, have we figured out how to lift something here? But one of the things Ingenuity has done really well is scouted out locations for travel for Perseverance. So this could go and scout out routes for Perseverance to go back and get those samples as well. And then Perseverance is the one that'll bring them back before they get shipped off. And so the new dates they also released, they're going to start putting in that preliminary design phase this October with the eye for a launch of the Earth Return Orbiter. So we can actually see the components of the mission here. Here's Perseverance. Here are those helicopters. We've got some satellites looking, and that Mars Ascent Vehicle will launch the samples up. It will meet with another spacecraft that will then return those back to Earth. So the launch of that Earth Return Orbiter and the sample retrieval lander will be in fall 2027 and summer of 2028. I promise you this is really fast in aerospace time. It's kind of killing me too. But the fact that they're still planning the mission and it's not a decade out is mind-blowing, right? And those samples then means would be back to Earth in 2033. 11 years, you can do it, you can hold out, I promise. And it is a complicated thing because this is a collaboration, which is great. It means NASA doesn't have to develop everything. And heck, we're using proven engineering, we're using Ingenuity, we're using Perseverance, right? But we do have to still let ESA design this return orbiter. They've now got spacecraft docking that have to come back to Earth. You've got to have this sample retrieval robotic arm, which is shown so nicely here. You still need a lander that is different from any other lander we've sent before, right? So we're speeding up the process a little bit. So hold on. I can't say this is going to be breaking news that we'll cover in 60 minutes anytime soon. But we are still going to keep covering the Perseverance rover. And it has now collected 9 samples. Yay. But it's also acting as a location scout for this future mission. Because we have this MAV, or this Mars Ascent Vehicle, right? We've got to land something and then it's got to launch back up. That launch back up piece is what we've not done before, right? So we need the most boring, uninteresting, pancake flat area of Jezero crater we can possibly find. And so they're looking at hazards that basically you need 60 meters or 200-foot radius, no sand dunes, no rocks more than 7.5 inches in size, and just nothing, and it all needs to be flat, not kind of angled at all. So we can do this somewhat from orbiters, but Perseverance is going to give us a much closer look. And so this really exciting image is fantastic because it is so unnotable. And this is what they're calling the landing strip. So this was a section of Jezero crater that had been identified before as a possible landing site and launch site for those sample return missions. And now we're getting a closer look. So this is one possibility to go on the short list. We'll probably see a few more possibilities come along, but Perseverance now is a rover of many talents, from helicopter entourage to sample collector to location scout. It's ready to go into Hollywood. So stay tuned there, and we should be starting to get some of that science with Perseverance coming out soon, now that we're starting to get those samples back. So for my last two stories, I want to touch on human spaceflight. We are still successfully operating the International Space Station. DMNS's good friend, astronaut Kjell Lindgren, is currently commanding the mission up there on the ISS. And NASA and Roscosmos have made a couple of interesting announcements in the last couple of weeks. So one of them is that they have announced a new ride-sharing deal, if you will. And so what this is that Roscosmos and NASA have come to agreement to swap rides. So if you remember, after the space shuttle was discontinued, we stopped that program, right? Up until the 2021 launch of Crew 1, NASA, JAXA, which is the Japanese Space Agency, the Canadian Space Agency, the European Space Agency, were all reliant on the Russian Soyuz capsule to get us to and from the International Space Station. Crew Dragon is the first time with SpaceX's capsule that we have returned to spaceflight. And now we've kind of separated. Russia and the cosmonauts from Roscosmos go up in the Soyuz, JAXA, ESA, Canadian Space Agency, NASA, all use Crew Dragon. But that's going to change. And so what they've announced is that NASA has 2 spots on future Soyuz missions. The first one slated to launch from the Cosmodrome in Kazakhstan in September. And NASA has assigned astronaut Frank Rubio to that. They've also assigned astronaut Laurel O'Hara for a later flight on the Soyuz capsule, which NASA astronauts are fully trained on. And for the first time ever, Russian cosmonauts are going to ride on Crew Dragon. So the first time this has ever happened, and the first cosmonaut to do that will be Anna Kikina, who's Russia's only active female cosmonaut. She will launch in September as well, along with 2 NASA astronauts and 1 JAXA, or Japanese Space Agency, astronaut on Crew 5. And they've also assigned cosmonaut Andrei Fedyev, I think I said that right. Ooh, I did not learn Russian, I learned Spanish, to Crew 6, along with several other astronauts yet to be announced. So why are we doing this? It's really about cross-training, right? So the ISS, as of right now, is still an international collaboration between NASA, Roscosmos, JAXA, Canadian Space Agency, European Space Agency. And one of the really important things is that everyone knows everything about that space station because it's reliant on one another. So what if something happens that an astronaut needs to leave early, or there's a malfunction with one of the vehicles? They need to know how to fly the other vehicle. It's a practical thing, right? You need 2 cars basically all times to be able to get home, and you need to know how to drive both of them. And it's also important for spacewalks and repair missions as well. So this is something that they feel it's really important that everyone is trained on all of those vehicles to maintain the safe operation and health and safety of all of our astronauts. So really exciting to see some new collaboration happening. Exciting to see the 1 female cosmonaut be able to go up to the ISS as well, to be able to continue that research that is happening there. But there is some question about the future of the ISS. This thing has lasted quite a while, right? And the US's plan is, to this point, to operate this through about 2030. And our goal ultimately is then to have commercial space stations that are up in orbit that will kind of help us bridge the gap as NASA looks forward to the moon and onto Mars with the Artemis missions taking us back to the moon. But yesterday, some interesting news came out. Roscosmos's head was just appointed this week after the last one was fired. And he has announced that they would like Roscosmos to exit the ISS by 2024. Or after 2024. In all fairness, the agreements from the international collaboration do end in 2024, right? And there is some question. Roscosmos, this is not the first time they've done that. They said, we're leaving early, right? Does this have teeth? The answer is we don't know. So when this was announced yesterday, it was about 45 minutes before a conference in Washington, D.C. was slated to start to talk about the future of research and development on the ISS. And at that point, NASA hadn't received official word. In fact, our friend Kjell Lindgren made a comment from the ISS saying, basically, we haven't heard anything official. The ISS is still an international collaboration. It requires all of the people on the ISS to complete this mission safely and successfully, and that is what we're going to do. So we don't know what this means. If Russia does exit this collaboration before the United States or other partners are willing to end the International Space Station mission, we don't know how long that could operate because Russia's segment's powered by NASA's solar panels, and the Russian propulsion sometimes boosts the ISS up. It really is meant to be this beautiful mingling together. So we'll see. Take it with a grain of salt. We'll find out what's happening. NASA still needs to receive official word of what's going on there. But NASA has been firm in their statements that what happens in space is still in the spirit of international collaboration. And they continue to do a lot of research up there, send missions up there, including those fantastic rideshare missions. And then from there, we'll see what happens. I mean, the ISS is cool, but it's not forever, right? We're looking to the moon, to Mars. There are other companies and other countries looking at space stations, including China, including Russia, and other exciting missions coming down. So spaceflight will continue. We are so excited for the next few Crew Dragon launches and those Soyuz launches, continuing that spirit of collaboration. And I want to end on a happy note. I always like to end 60 Minutes in Space by pointing out how you all can get involved in astronomy. And the easiest way for this is to look up into the night sky. And this month happens to be a pretty darn good month for that. So after the planets all having been beautiful morning objects, I'm sorry, early birds, we astronomers are getting them back in our night sky again. So if you like to stay up a little late, Jupiter and Saturn will be joining the night sky. About mid-month, Jupiter rises at about 9:30 p.m. So not super early, but it'll be there. And Saturn is at what we call opposition, meaning that it is opposite the sun from Earth. It is the most bright, you will see it all year. So even with binoculars, you can see moons of Jupiter, and with small telescopes, you can see rings of Saturn, bands on Jupiter as well. So take a look. And then August 12th, the old faithful of meteor showers comes back, the Perseid meteor shower. We typically see about 60 shooting stars or meteors per hour. This is debris from Comet Swift-Tuttle. Now this year, unfortunately, we also have a full moon, which means that it's going to be a little washed out. You won't see the full 60 meteors per hour, but it's worth a look. Go look a few days before, a few days after, whenever you can get it clear, and just sit back, lay back. It requires no special equipment, and look for those meteors and get as dark a sky as you possibly can. And so with that, I would like to turn it over to any questions that you all have and open it up for Q&A. And thank you all so much for joining us. And Jessa's got a microphone. If you have a question, you can raise your hand. She can bring that to you. I don't know if we can take questions from folks on Zoom or not.
We can.
Excellent.
Getting them.
Don't be shy.
There's
one. All right. So you mentioned Z13, the redshift number.
Yeah.
Can you talk about that system and how it works?
Yeah, so redshift we note by the letter Z. Very exciting, right? And so what that is it's looking at basically, and I forget the exact measurement, my apologies, of how far that spectra is redshifted. So we look at really specific elemental lines, and we can quantify how long in a wavelength it has been shifted to the red. So the bigger the number, the more the redshift is. So Z of 13 is right on the edges of the universe. Z11 was the last one that Hubble observed. And then close to us, you get a Z of 0, basically, right? So that's kind of our functional scale, but it is a measurement of how far those spectral lines are shifted into the red and infrared and beyond. Yeah, and then you can do, using the Hubble constant, do a calculation and convert that to distance. It gets a little more complicated. Don't make my students do that. I'm nicer than that. Yeah.
I know it's a silly question, but I'm curious.
No, I love questions.
So we have the colorization.
Mhm.
What colors are truly out there?
What colors are truly out there? That's a great question. So I'm going to bring back a slide that showed the visible light of that lovely phantom galaxy, right? this is pretty darn close to true color. So stars emit at different wavelengths of light in the visible part of the spectrum, depending on their size and their temperature. So blue stars are really, really hot. They also tend to be large and massive. They're the rock stars of the universe. They live fast, they die young. They are really cool stars, cool in the colloquial sense, not in the temperature sense. Important distinction, sorry guys. We have a great, nice big red star there. So if you've ever seen Betelgeuse or Antares or Arcturus in the sky, those are red supergiants. Their stars also kind of middle of the road stars, middle-aged stars like our sun emit kind of yellowish color. And then we also have emission and reflection of gases, right? So those bright stars are giving off light that can be reflected off of gas. So we might see some reflection there. We also might see some red emission from hydrogen as well. So a lot of different colors that are out there, and the Hubble pictures really do try and stay true color, even though they're false color. But in the cosmos, we're seeing blues, reds, yellows, whites, and all sorts of things in between. That's a great question. And I was just thinking, if you look at the Carina Nebula image, there's some great colors in there, or this was the other one from James Webb, which is not a true color image because it's infrared, but these planetary nebulas, you do often see a lot of blue and then a lot of yellow and red. So that's not totally out of the question.
Great. We do have a question from our online audience.
Yeah.
If Russia is ending its involvement with ISS, will that cause any delays with any of the Mars missions?
So if Russia's ending its involvement with the ISS. So yes, ESA, and not because of the involvement with the ISS, but the European Space Agency has made the stance that they will not be launching their ExoMars rover as planned because it would rely on a Russian rocket. And so they are delaying that possibly out till 2026, 2028. That was a political decision not tied to the ISS, but something that the European Space Agency took a stance on. So we are seeing Earth politics affect space. Roscosmos also kicked NASA off of the future Venus mission, Venera D. We'll see how it plays out, but not tied directly to ISS.
Hi.
Hi.
Elon Musk said some time ago that it is possible that it will be, in order to terraform Mars, we should consider nuking the poles of Mars in order to release CO2 and create a greenhouse, a greenhouse effect and accelerate the terraforming process. How realistic is that? And has there been any talks behind the scenes about actually doing it?
Yeah, so terraforming Mars is a really fun board game where you can nuke the poles and safely. But in real life, it's an interesting question because there's two factors to it. There's a reality and scientific possibility and a morality, right? So terraforming Mars will take hundreds of years, even with doing something as extreme as Elon Musk is proposing, right? It is going to take time to build up the cycles that we are used to. In addition, Mars has no magnetic field, right? So the reason Mars looks the way it does is once that core cooled, that magnetic field was gone, it basically stripped that atmosphere away. So now we also need to build a way to protect this new atmosphere that we've just created and to be able to sustain it. And there's been talks of magnets or things in between the sun and Mars to try and protect it from solar wind and the bulk of the cosmic radiation. It's a long way off. And then we have the moral side. Perseverance is out there looking for evidence of past life. What if we find it? What right do we as humans have to vastly change another planet, if there's even the possibility of life being out there? And that's something the Office of Planetary Protection looks at on a regular basis. This is NASA, it's a real office. Don't Look Up got that right as well. And so one of the things we look at is contaminating other planets, right? We don't want to bring our microbes there, nor do we want to bring them back if they exist. So terraforming brings up an interesting and complicated set of engineering and scientific principles, but then we've got to take that moral aspect in, and no one's ready to answer that quite yet. Good question, yeah.
Hi, thank you so much for being here. I really appreciated all of this and your expertise and your wisdom. I'm wondering, what is the scientific reason or value for spirals in galaxies? Is there, like, it's a very consistent pattern also in nature. So I'm curious on like how, like what that means for space.
Did you go to Numbers in Nature, the exhibit here, a year ago? Ah, that would have been perfect. We talked a lot about spirals at that exhibit, a temporary exhibit here. So in terms of space, spirals are an interesting thing. We don't fully understand how they formed yet. And so one thing that we think has happened is that it's density waves that happen. So think of it like traffic on I-70, right? If you're local here, right? You get those times where you're driving clear through, everything's fine, and all of a sudden it's stopped. And you're like, what is going on? Is it because there's a curve? Is there something happening? And then you get to the other side and there was nothing there and you move through, right? So that's kind of what's happening with galaxies, is that material is moving through these density waves where they get packed up and let out. Why? Good question. So that gets to the idea of how did these spirals form and start? And that's something that's still being investigated. If you're interested, there's a really great video out there by SciShow Space, which is a PBS spinoff that talks about how spiral arms form. But we see them a lot in nature. They often reflect the Fibonacci sequence and other mathematical principles as well, which is really fun and interesting. And totally find the Numbers in Nature exhibit if you can, because it was great.
So James Webb's already discovered things that haven't been seen before already. I'm wondering, is it gonna see things that, new kinds of things that haven't been seen before, like star systems with 8 or more stars, or moons with moons, or things that make adjunct astronomy professors say, what is that? We need a new definition for that new type of object.
That's a great question. Wouldn't that be cool? Oh, I want that to happen now. So that's a good question. I mean, so James Webb is going to allow us to see into regions of space we really haven't seen before. So we're pretty secure in our principles of, say, like star formation, for instance. So if we look in a star forming region, there might be an aspect of it that we haven't seen before. Like there's a really brief stage in star formation where we get what we call proplid, a little protoplanetary proto-star disk. And this cosmically happens in the blink of an eye. And it's so obscured in dust, we can't see it well. So to see something like that, while it's not something we don't know exists, but to see it in clarity would be mind blowing. And I'd be sitting here going, oh my God, we saw a baby star. That's so cool. And so there's a possibility. I don't think we'll, in terms of planets, the questions you asked there, it would have to be in our own solar system. Exoplanets, it's not going to directly image. We're really looking at spectra of atmospheres. But what if we found one of those Earth-sized planets that had an atmosphere with oxygen in it? Also would be jumping for joy. So many reasons to make an astronomer jump for joy. I think that's a good reason.
Can you explain why we haven't been back to the moon, and what are the plans coming up to go to the moon, and when is that?
That's a great
mission?
question. So obviously Apollo, we went to the moon for the first time, 1969. Apollo 17 actually was the last mission, and we'll hit its 50th anniversary this December. So then the focus from there was really about those big cargo vessels, the shuttle, to get us into Earth orbit, to build things up there, to internationally collaborate. And the moon politically is a hard thing to argue for. We've been there, right? We send rovers there. Why, when there's not a huge race and a really fascinating set of political circumstances, would we go back? So the push then came to go back to the moon and then on to Mars with the Bush administration in the early 2000s. He announced the first Moon to Mars plan, and it was this big thing to try and get everyone around this together. And since then, the Bush administration modified it, the Obama administration modified it, the Trump administration modified it. The Biden administration hasn't touched it yet. He's had a big pandemic to deal with, right? So we don't have that continuity of plan. So we've been building the Orion spacecraft and the Space Launch System since the early 2000s, but the mission parameters keep changing, which makes it really difficult to build a spacecraft for. But we should see a test of SLS any day now, I hope. And so it's been hard. But the plan basically is to, with the Artemis missions, as the name, is to send the first female astronaut to the surface of the moon and to build a lunar gateway, which will be kind of a space station orbiting the moon that can serve as a base of operations for more long-term missions to the surface of the moon. Missions Artemis 1 should launch here in the next couple of years on uncrewed, crude being crew ED, not crude as in crude oil, but uncrewed, right? Because we're not saying unmanned because we're sending a woman, right? And then we should be returning mid 2020s to early 2030s. That timeline keeps slipping. We'll see, but they have announced the NASA astronauts that are going to be part of this. Our friend Shel Lindgren is been assigned as an Artemis 1. Frank Rubio, who's going back up to the ISS, is an Artemis astronaut as well. So longer term operations of the moon, possibly. Good questions. Two questions from the front row people. Love it.
How big would the accretion disk of the black hole be to control the phantom galaxy?
How big would the accretion disk be of M74? All right, you got me thinking. All right, so the accretion, we're going to talk this out loud because this is how I work. All right, so M87, which is the big elliptical galaxy at the center of our galaxy cluster, is the first one we imaged, right? Its accretion disk is bigger than the solar system. So it's gonna be smaller than that. I don't know. I'm gonna have to look that up for you. Can I look that up? Oh, I like it. Can I look that up for you? Can we explore that together after the program and find an answer for you? Does that sound okay? Thanks for stumping me. I like it. Good questions.
How exactly will Curiosity give back the data?
So how is Curiosity getting back the data? All the Mars rovers, right? So you mean like the samples that, not the physical samples, or like just the information they're getting? The physical sample. So you're thinking Perseverance, right? So Perseverance actually has a rock hanging out with it right now, but that's by accident that it has a pet rock. Wind is a fun thing. But what it'll do is it has a robotic arm that'll be able to retrieve those samples. And I don't know exactly where on the spacecraft they're going to put it to store it safely. But it will use that robotic arm, which has a claw on it, basically, to pick those up and to take it with it over to the sample lander, where it'll set it down. Another robotic arm will come and pick it up and put it in its safe spot and take it there. So it's all about this robotic arm, which is a really cool arm. And just like our arm, it has joints, right? It has a shoulder, it has an elbow, a little bit of a wrist, and then it's got all these cool instruments on the end. And unlike our wrist, it can rotate in funny ways. I can't do that. But one of those things is that it can actually grab those. And so I'm not sure where it's going to store those because that's a new part of the plan, but it's going to use that robotic arm and get information from NASA here to say, hey, you need to go to this location. And it sets its course. It drives a rover, just like you can kind of drive a rover in Space Odyssey, right? You got to send it a set of instructions to get to that place, pick it up, and bring it back. Does that answer your question? And then there's going to be a rocket that'll all go on to meet an orbiter. And that will then fly back to Earth, land on Earth, where the scientists will come and grab it. And then we'll be able to study it. Is that good questions? All right. One more question? Yeah, we have time for one more.
I was just wondering if the new telescope would be able to see any other planets within like that Goldilocks zone. Will it help identify more, or because it's so far back, they wouldn't be in the Goldilocks zone?
So we can actually see a variety of extrasolar planets. The ones being in the Goldilocks zone are obviously the ones we really want to know more about, right? So we're using satellites like TESS, the Transiting Exoplanet Survey, to be able to find those planets. And then they're just really hard to image for a couple reasons. One, you've got that big bright star in the way that's overpowering the light that we get from the small planet. And so you actually need a specific tool called a coronagraph to block out the light from that star to be able to see the light from the planet and directly image it. And that's another mission that NASA's working on. So that's going to be happening. So we won't get images of it, but what we can do is get those cool spectra of the atmosphere. So we can take information from Kepler, from TESS, from ground-based telescopes. Now put that together with this huge missing chunk of, we think it's Earth-like. We can measure its mass, but does it have an atmosphere like Earth? Is there water there? And James Webb can pull out that piece of information and put it all together to really give us that complete picture of what that planet might look like. Even if we can't see it as cool as the planets in our own solar system, it'll be a dot still, but we'll know a lot more about it. That's a great question. It's actually really hard to do. really hard. Yeah.
Great. Thank you so much, Naomi. Can we get a round of applause for Naomi?
Thank you.
It's a pleasure to have you back. Thank you all so much for coming. Please join us next month, Wednesday, August 30th, either here in Ricketson at the museum or virtually. So thank you all so much. Have a great night.
Thank you all.